Hello everyone, this is tutorial number 3, Chemical Reaction Engineering, chapter of Red Laws. In this tutorial, we're going to solve two different questions. In question number 1, we're going to solve a problem related with Red laws and equilibrium constant. And then on question 2, we're going to solve a question related with kinetic parameters such as activation of energy, frequency factor, and also the red constant. Let's see problem number 1. In this question, we will have a reaction A goes to B for part A, and it's mentioned that it's irreversible at low temperature. However, we will have a reversible reaction at high temperatures, since this is a highly exothermic reaction. So the question is, suggest a red law for each of the reaction in part A and B at high temperature. In each case, make sure the red laws at high temperature are thermodynamically consistent at equilibrium. In order to solve the problem number 1, part A, we need to assume a form of the red law for the reverse reaction that satisfies the equilibrium condition. So we can start from the net rate. So at low temperature, we're going to have a forward reaction. So we can write it A goes to B, and we will have the red law for forward reaction is going to be equal to minus K1Ca. So in here, the A will be consumed, so Ra is going to be negative. And then at high temperature, we will have reverse reaction. So B is going to be consumed to produce A. So if we write it in terms of A, we can call it Ra reverse. It's going to be positive K1Cb. And then the net red law, which is both forward and reverse reaction, we can write it in terms of Ra net. It's going to be equal to Ra forward plus Ra reverse. So what it means, if we write it in terms of Ra, it's going to be minus K1Ca plus K minus 1 Cb. And then of course at the equilibrium, thermodynamically, we will have the equilibrium constant will be the concentration of product at the equilibrium divided by the concentration of reactant at equilibrium. So what it means, if we look at this, we will have K1 over K minus 1. And we should remember that at equilibrium, the red law, it's going to be 0. This is why we will get equilibrium constant equal to the constant rate for the forward reaction divided by constant rate of the reverse reaction. So if we go back again to the form of net rate law, we will have RA, negative RA equal to K1 CA minus K minus 1 CB. And then if we remove it outside the rate constant, we will have K1 times CA minus K minus 1 over K1 CB. And then based on the equilibrium constant definition, now we can write RA as K1 CA minus CB over KC. And then if we implement the equilibrium condition, we will have Kc at the end will be equal to Cb, which is going to be at equilibrium, over Ca at the equilibrium. So this satisfies the equilibrium condition. For the question in part B, we will have the reaction of A plus 2B goes to 2D. It mentioned that it's irreversible at low temperature, and the rate law is going to be negative RA equal to KCA CB to the power of 2. And it applies the same condition with the part A, that this reaction is going to be reversible at high temperature. So in order to solve the problem in part B, we will do the same steps with the part A, which is we're going to write the condition at low temperature. We are going to have forward reaction, which is A plus 2B becomes 2D. And here we can write the RA for forward reaction is going to be equal to K negative K1 multiplied by Ca Cb to the power of 2. And then at high temperature, we will have reverse reaction where 2D is going to be consumed to produce A and B. And then we are going to have the rate law for reverse reaction. It's going to be K minus 1 concentration of D to the power of 2. If we go back to the net rate law, we have negative RA equal to K1 CACB to the power of 2 minus K minus 1 CD to the power of 2. And if we try to put K1 outside, we're going to have this form. And then if we apply the terms of equilibrium constant, we will have the rate of A at equilibrium, which is equal to be 0. It's going to be equal to K1 Ca Cb at equilibrium to the power of 2 minus Cd at equilibrium to the power of 2 over equilibrium constant. And of course, we will have our equilibrium constant will be equal to CD to the power of 2 at the equilibrium over CA at equilibrium, and then CB at equilibrium to the power of 2, and this satisfies the equilibrium condition. Now let's go to the question number 2. In this question, we have a reaction 2A plus B goes to 4C, and we have the information of concentration of A 2 molar and concentration of B 1.5 molar. We also have information of the rate of the reaction of A at different temperature. So the question is to calculate the activation of energy, the frequency factor, and also to find the rate constant as a function of temperature using temperature of 300 Kelvin as the best case. In order to solve this question, we need to use all the information that we have. Since we have the information of the rate of the reaction at different temperature, and also we have the concentration of A and B, we can find the K value for different temperature. And then later, if we use the information of K value and also the temperature, we can find the activation of energy and also the frequency factor. In order to solve the problem in part A, which is the activation of energy, first we need to derive the rate law. So the rate law, we have a reaction of 2A plus B become 4C. Based on the elementary rate law, we will have RA equal to KCA to the power of 2 and CB. And then, if you remember the rate constant formula, we have reaction or rate constant equal to pre-exponential factor multiplied by the exponential of energy activation over RT. If we try to linearize this equation, we can have ln K equal to ln A exponential minus E over RT. And then if we're breaking it down, we will have ln K equal to ln A minus E over R 1 over T. If you look at this equation, this is resemble the linear equation B plus mx, where m is the gradient of the line, B is ln A, and x basically 1 over T. So if we have a data of ln K and also 1 over T, we can find the energy activation and also A from the equation of line. Based on the information that's available, we have the value of RA at certain T. So what it means, we can calculate K, which is going to be equal to RA over CA squared times CB. So we can have different K at different t. And if we have t, we can calculate 1 over t. And since we got k, we can also calculate ln k. And then when we have this information, we can plot the value of ln k and also 1 over t. Based on my calculation, we will have a line that looks like this. I put the calculation of k, 1 over t, and ln k in the Excel. And then we have previously these two data, which is minus RA and t. So we will get the value of 1 over t and ln k. And then if we plot it into this graph, for x it's going to be 1 over t, and then for y ln k, we will have this line. If you look at the line, this is basically a perfectly a linear plot. So what it means, based on the equation that we derive, which is linear equation, now we can calculate the gradient of the line, which is m, and it's going to be equal to E over R based on this equation. And then if you remember the linear equation, how to find the gradient, we can use 2 point. So we can use 2 point y2 minus y1 over x2 minus x1, which is actually delta y over delta x. Based on this plot, y is going to be ln k and x is going to be 1 over t. So we can choose two different values, for example, the first value and the second value. So we can find m should be negative in here, negative E over R. It's going to be equal to minus 4.87 minus 8.01 over 0.003, this value, minus 0.0033, which is this value. So now we can get m. If you calculate, we will get about 150.372. And then if we use R equal to 8.314, we can easily find the energy activation. It's going to be equal to 128.79 joule per mole, or it's about 125 kilojoule per mole. So as soon as we get the energy activation, now we can calculate the frequency factor, or A. Again, we can use the same formula, which is ln k equal to ln A minus E over R multiplied by 1 over T. We can choose any point. We can choose, for example, choose data at 300 Kelvin. So based on this, we can calculate ln A is going to be equal to ln K plus E over R1 over T, which is going to be 300 Kelvin. So based on this, if we calculate, we will get ln A is going to be 42.1565. And then if you remove the logarithmic natural, we will have frequency factor about 2.0339 10 to the 18 mole to the power of 2 seconds. The last question from question 2, which is part C, is to find the Red's constant function, or K. So we can use the formula of K, which is depend on temperature. It's going to be A multiplied by exponential of minus E over RT. Of course, now we have A, we also have E. So if we put it together, we're going to have K as a function of a temperature, which is 2.0339 multiplied by 10 to the 18 exponential 50.372, which is this is E over R over temperature. And then if we use T naught as a best case, which is at 300 Kelvin, we can find K T naught based on the equation above that we already get. We will have K T naught equal to A exponential minus E over R T naught. We're going to have 0.00033333. And then if we put it as a formula with a base case, we will have K T naught, which is this number, multiplied by exponential E over R multiplied by 1 over 300 minus 1 over T. So now we can easily find the value of K at different temperature using the base case of 300 degree Kelvin.